Sebastien Fromang on are MRI simulations reliable? We almost. Thank you very much, Sebastien.
Shortest talk of
Thank you. So, good morning, everyone. So, in this talk, I deliberately choose quite a bold title to strike your interest. I'll try to review what we've learned in the last few years, 2 or 3 years, from doing simple local numerical simulation of the MRI in a very idealized environment. And I will try to describe what changed in our view of the MRI compared to what was thought since the early 90s, and try to discuss at the very end the consequences that may occur for the topic of this meeting, planetesimal formation. So it's works that I've been doing with many people. So this talk can only be put together thanks to many people. Some of them are in this room, and so I listed all the people that contributed one way or the other to this talk, either through direct interaction or discussions or emailed interactions. So here's the outline of my talk. It will be roughly divided in 4 parts. In the first part, I'll present mostly the facts, and mostly unstratified sharing boxes simulations that I have done or that other people have done. Then I'll try to discuss some recent results that have been recently obtained when trying to improve the realism of this simulation and the difficulties of doing so. And then the third and fourth part will be more speculative, and I'll discuss the issue of numerical convergence of this simulation, which actually got me into this problem, and that is now studied by many. And then I'll try to see how reliable your simulation is when it comes to planetesimal formation. So let me briefly mention the numerical setup. I suppose many of you are familiar with it. What we do is we start from the statement that global disk simulations are far too complicated, so we simplify the problem by considering only a local patch in the disk. And we work in the local approximation, that's the so-called sharing box model. So it's basically a local expansion of the MHD equation. So depending on the situation, I'll include or not explicit dissipation. What we usually do is to make the problem even simpler. We forget about all the thermodynamics, and we assume that the equation of state is isothermal. And to make it even simpler, we forget about the fact that we have a vertical stratification orthogonal to this midplane. We neglect that, which amounts to looking only at the structure of the flow close to the midplane, and that's the so-called unstratified sharing box. So in most of the simulation, I will neglect vertical stratification. And usually we take elongated boxes in the toroidal, the azimuthal direction, to take into account the fact that structure in general are distorted by the background shear flow. So one peculiarity of this in this talk is that I will speak a lot about small-scale dissipation. We heard about it already from Mark's talk. I'll only consider ohmic dissipation, ohmic resistivity in this talk. And this small-scale dissipation, associated with it, you can define dimensionless numbers. And basically, there will be 3 recurring numbers in this talk. The Reynolds numbers, which is defined as the ratio between the sound speed, the scale height of the disk, divided by the viscosity. And again, it's a small-scale viscosity. The magnetic equivalent is the magnetic Reynolds number, where you replace the viscosity by resistivity. And then you have a third number, the magnetic Prandtl number, which is the ratio between viscosity and resistivity. So those are the three numbers that are going to come. So when you do this sort of simulation, you start with a gas flow which is in equilibrium. You add a small magnetic field to the equilibrium flow, and because of the MRI, this magnetic field is going to destabilize the flow, and you watch the turbulence grow, and then you study the properties of this turbulence. So what we found is that, in general, the structure of this turbulent flow depends somewhat on the structure, the topology of the magnetic field that you put initially. And there are essentially two broad class of magnetic field configuration, which depends on whether you have a mean magnetic field that goes across your box. So if you have so the first situation corresponds to a case where you have no such field in either direction crossing the box. So that's the zero net flux situation. And this case is somewhat peculiar because if you let this situation relax and there is no dynamo process because of dissipations, you expect the field to disappear, magnetic field to disappear. So if you have sustained turbulence over a long period of time, it means that you have a dynamo effect happening in your box. So one of the issues is to understand if such a dynamo process exists, what it is, and what this process is. And then we want to know about the saturation of this dynamo, if it exists. The second broad class is the one where you have a mean magnetic field threading your box. And you can have a magnetic field threading your box in a toroidal direction or in the vertical direction. And here the situation is different because you have normal MRI modes that destabilize your flow all the time and that keep regenerating the turbulence. Because of the peculiarity of this sharing box, we use periodic boundary conditions. You cannot lose that flux. And so you keep regenerating the turbulence. And again, we want to look at the saturation of the turbulence in this situation. And there are also peculiarities associated with the net flux situation. There have been lots of interest in the role of parasites in this situation, and Pierre is going to talk more about it. So now let me move on to the numerical result. And focus first on the zero net flux case, in which we usually start with a vertical field, which is sinusoidally oscillating with radius, such that the mean vertical field is zero. So we then add a small perturbation to the field and let the flow relax. So what I did basically a couple of years ago was to take Zeus out of the web, use it in a so-called ideal MHD approximation, one in which you have no explicit dissipation coefficient, and you can run the sharing box MRI in this situation. And that's what people have done for many years, and since the early 90s, it was found that here you have a plot basically that shows the time history of the alpha parameters that we've heard a lot already about in this meeting. So what you see in this plot is that as a function of time, because of the MRI, you get a non-zero alpha value, which is oscillating around a well-defined steady state. Okay, so that's the typical outcome of such simulation. And the typical alpha that you get out of such simulation are a few times 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ grid cell per scale height. So here the box is a box of size 1h in the radial direction, 1h in the vertical direction, and about 4h in the azimuthal direction. So now I got into this not because of me being clever, but because computer got bigger. And at the time I studied that, you could do higher resolution stuff. And when I doubled the resolution, I saw that alpha was going down by a factor of 2. That's exactly the same simulation, just the resolution is increased. And when you double the resolution again, it seems to be going on. So the question is it physical Or is it a numerical artifact? Does alpha goes to 0 in real disk when the Reynolds number is very large? Or are you just seeing something numerical? So in any case, whether or not it's a physical effect or a numerical artifact, the only thing you change here is the size of the small cells in your grid. So it seems to be affecting, so what happens at the scale of these cells is affecting your result. So you want to treat those scales properly. So it means that you have to introduce explicit dissipation in your simulation if you want to avoid the numerical scheme of your code to take care of the result for you. So that's how we interpreted this result as a need to introduce explicit dissipation coefficient in the simulation. So I'll come back into this issue of numerical convergence afterwards. When you do so, when you introduce explicit dissipation coefficient in Zeus, for example, you have to make sure that this explicit dissipation coefficient that you introduce dominates over numerical dissipation. And that's not straightforward. You need to be quite careful. And one of the things we did, among others, was to take a set of parameters. So here's the magnetic Prandtl number. Here's the Reynolds number that he introduced. And we did the same simulation with many different codes. And we checked that this is a well-posed problem. So for every code having those parameters should find the same answer. And more or less, you get alpha of the order of 10 to the minus 2. So you have an acceptable agreement over a broad range of methods, of numerical methods. So that gives you confidence that you are properly resolving your flow. One of the things we did also on this setup was to test for the effect of the box size. And here you have two runs performed, one in the standard box we use and one in which the box is elongated in the radial direction. And pretty much we found the same answer. Here's the time history of alpha in the two calculations. And you see that there is very little difference. So the effect of the box size doesn't seem in this situation to be important as long as you take elongated boxes in the azimuthal direction. And this is a result that seems to pertain in stratified boxes when you include vertical stratification. So now we know we have a better handle on what explicit dissipation we are allowed to take at a given resolution. We can scan the space parameter and see how the saturation level of the turbulence varies as a function of this dimensionless number. So one of the things I did was a set of numerical simulation where I fixed the magnetic Reynolds number and I varied the ratio of viscosity over resistivity. So here's the standard case you had before with the time history of alpha. So you have alpha being of the order of 0.01, 10 to the minus 2, the standard value. If you double the Prandtl number, now you see an increase of alpha. If you go to even larger Prandtl number, you again see an increase of alpha. If now you go to the other direction, with a PM equal 2, then you see that the activity goes down, and eventually after about 90 orbits, it disappears. No turbulence anymore. The flow becomes laminar, and the situation is even worse at lower values of PM. So the conclusion we got from that is that alpha is an increasing function of the magnetic Prandtl number. And we found for these particular values of the Reynolds number, we found no MHD turbulence for small values of PM. This is a bit worrying for our problem, the problem of protoplanetary disks, because the value of PM in this disk is extremely small, 10 to the minus 5. But note that there is a difference with this stuff, that the Reynolds number is very large. It's 10 to the 10 or 10 to the 15. So it's this regime of parameters is very difficult to access from numerical simulation. So that's something to keep in mind when you look at these results and when you try to deduce consequences for protoplanetary disks. Now let's come back to the convergence issue. So, and assume that it's not a numerical artifact, and that in fact what you're doing when you increase the resolution is that you decrease your numerical dissipation. And more or less, you will increase, you expect that you decrease the viscosity and the resistivity in similar ways when you increase your resolution, each time you increase your resolution. So you can interpret this result, and that's the good scenario, I'd say, one in which numerical dissipation is behaving in a physical way. You can interpret this result as saying that alpha decreases when the Reynolds number increases at roughly a fixed with a fixed ratio of viscosity over resistivity. Because what you expect to be doing in this scenario is going from here to here, you decrease viscosity and resistivity roughly in the same way so that their ratio is a constant. So that's a possible interpretation of these results, and just do it. Now that we have explicit dissipation, we can take the same code, start with this set of parameters, and then increase the Reynolds number, keeping the Prandtl number fixed. So that's the structure of the flow you get in such a simulation. So that's, again, for the same parameter. So of course now when you double the Reynolds number or decrease your dissipation coefficient, you also have, it comes with a price at increasing your resolution. So each time I double the Reynolds number in this experiment, I increase the resolution by a factor of 2. So that's the first part. So actually this snapshot is not as good as on my screen. So you see that you have more and more structure on your flow. So that's with a Reynolds number of about 6,000, and here the resolution is about 256 per grid cells. And you can double the resolution again, and here you get even more structure in your flow. Note that this is extremely time consuming. It's 500,000 CPU hours, about 3 weeks on 1,000 processors. It took me a year to do it. But it's doable. And now with this set of simulation, you can study what it does, what the transport properties are. So here's the time history of alpha for the standard run. So again, you find something that is roughly 10 to the minus 2. So to reduce the computational cost of this simulation, what I did was to restart, at some point, restart the simulation by decreasing the dissipation coefficient to produce the two other runs. So that's the second simulation. I restarted it here and decreased the dissipation by a factor of 2 and let it relax. So you see that it takes about 20 orbit to relax, and then you have a new steady state with an alpha value which is comparable, a little bit smaller. And I did the same to go to the third simulation, and this is what you get. Again, you have a phase in which the flow is gets relaxed, and then it seems that you reach a steady state. And the puzzling result is that there is no sign of a systematic decrease or increase in this simulation. It's consistent with the angular momentum transport being constant as you increase the Reynolds number with a fixed PM. Okay? So it's different from simulation without explicit dissipation, which are qualitatively different. And it suggests that those simulations are not telling us something meaningful about the physical behavior, or at least the simple interpretation of this simulation fails. And it suggests that these simulations suffer from a numerical artifact rather than being physically interesting. So now you can look at the high resolution in more detail. And here is a plot of the power spectra of the kinetic energy and magnetic energy. And the new thing you get from this simulation is that there is a range in wave number in which the kinetic energy shows a power low, which is close to minus 5/3, which is the Kolmogorov scale, the Kolmogorov low. So one way to interpret this is to say that you start to see a small inertial range in your simulation. The other thing you get from this power spectrum is that you see that you have a bump at about this wave number here, which is roughly the start of this so-called inertial range. I wouldn't bet too much money on this exponent here because it's still a pretty small inertial range. But you have a well-defined wave number when this polar behavior ceases, and you can argue that in hydroturbulence you would identify this wave number as being the location where you inject energy in your flow. So you have a signature that you have a well-defined injection length in this flow. Now you can go back and look at knowing this result, you get more convinced that you see this inertial range also in the low resolution simulation, and also with a well-defined injection length that seems to be at about the same wave number. So to get a more quantitative estimate of where the energy is going down, is coming from, you can look at the equation for the mechanical energy and how it varies with time. And this equation, this mechanical energy has a source term, which is basically proportional to the shear, because that's where you're extracting the energy from, and proportional to the total stress that's exerted on the flow. And that's the sum of the Reynolds stress and the Maxwell stress. And the dominant term is the Maxwell stress in MRI simulation. So this term is coming from the induction equation. And you can look at how this term varies in Fourier space by taking the Fourier transform of this equation and take the dot product with B phi. So that's the complex conjugate of the Fourier transform of B phi. So you see that this term, so to get a feeling of where the energy is coming from, you need to look at this term in Fourier space. So that's what I did. For the tree simulation, you see that this function peaks at the same location. Okay, so that's another hint that you have an injection length that doesn't depend on the Reynolds number, and that corresponds to scales of about a third of the box size. That can be contrasted with an estimate for the location of the dissipation scale that you can try to estimate by looking at the product of k squared, bk squared. And as you increase the Reynolds number, you see that the peak of this curve is shifting to smaller and smaller scale. It's what you expect because you decrease dissipation. So you decrease the dissipation coefficient, so you expect you'll dissipate at smaller and smaller scale. So we did a complete parameter survey of this situation. And here they are summarized in the Reynolds PM plane. And you see that in some of the case we find that the flow is turbulent, in some others it isn't. And you can draw a line that shows the separation between turbulent and non-turbulent situation. What is important two things are important to remark. There seems to be a critical Prandtl number over which you have active turbulence. And this critical Prandtl number seems to be decreasing with RE, the Reynolds number. However, we don't know what happens for a large Reynolds number. And protoplanetary disks, they are somewhere here, or maybe even further away. Okay? So we're very far from the good regime. So another way to plot this result is in the RE-RM plane. And the reason why I did so is that it's the plane that people studying homogeneous MHD turbulence often use. And for example, in this paper by Alex Chekochin, you'll find such a plot summarizing the result. And here they look for an effect of dynamo. They look for dynamo action in homogeneous turbulence. And where it's green or yellow or red, it indicates that dynamo is growing. So they also can draw a line in this plane separating the dynamo versus non-dynamo situation. And you see that so you want to look at this line, which is this critical line. And you can draw a similar line in R for our result. So now you see that at small values of PM, so large RE but low RM, they are now starting to see dynamo activity. So this curve is going down. So you can wonder what happens in our situation for the MRI. Do we have such a behavior, which would then mean that we have turbulent activity at low PM, which would be the regime relevant for protoplanetary disks. So this is a question that is important to solve. So now let me move on to toroidal net flux. So here you start with a pure azimuthal flux, a pure azimuthal field. So is there a PM effect? So I took a good enough code to check that. I did my quick and dirty calculation of that. I did 3 runs varying the Prandtl number for just one value of the Reynolds number. And you see an effect of the Prandtl number on the saturated state. So again, it's the time history of alpha in the 3 simulation. So Jake Simon and John Holley did a much more thorough coverage of the parameters and recently put on AstroPH their result. So here's what you get. It's alpha as a function of PM, summarizing all of their parameters. And again, you see that this result broadly show an increase of alpha as a function of PM. It's interesting to look at their PM equal 4 case, which is similar to what I've described before. And you see that there is a very small scatter here of their run for this value of PM. So it's consistent with the results that I just described. Another way to look at this result, which is rather messy at first glance, is to plot alpha as a function of the Reynolds number. So here different symbols corresponds to different values of PM. And you can draw a line on top of this diagram, which are lines of constant PM. And again, so this is the PM equal 4 curve, 2, 1, 0.5, and 0.25. So there are hints that as you increase the value of the Reynolds number, things start to converge. So it's true for the PM equal 4 and 2 case. You're starting to see that for the PM equal 1. So it's too early to make definite statements, but I used to be very pessimistic about this whole problem. And the recent result I got associated with this is making me a bit more optimistic. So the conclusion is that although you have a dependence with PM in this case, it seems to be a bit weaker than in the zero net flux case. An interesting point is that they found sustained turbulence for low PM, 0.25, thanks to the toroidal flux constantly forcing the flow. So that's a difference with the zero net flux. And there are hints of convergence. So the third situation is one where you have a vertical net flux. So again, you can wonder, do you have a PM effect? And again, you'll be no surprise if the answer is yes. So it's something that Geoffroy Le Sueur and Pierre-Yves Longarity has found in 2007. And Pierre-Yves is going that. So there are specific issues associated with this case. And Pierre-Yves is going to make a full talk on this situation, and he'll give you new results that they recently got on this problem. So I'll not speak more about that. So what seems to him, the comparison you can make between these results and homogeneous turbulence and the strong effect with the Prandtl number suggests that there is a link between MRI-driven turbulence and small-scale dynamo. To be more specific, when in small-scale dynamo, they got exactly the same as we do, except they've done it better because they've done it for longer. And in the large PM case, they easily see dynamo growing, and that's the structure of their flow. And the reason why they easily see dynamo is that in this situation, the viscous length is much larger than the resistive length. So you have large eddies in your flow, and you can roll up the magnetic field in these large eddies and stretch it and make the magnetic field grow in these eddies. So you have an efficient way of amplifying the magnetic field. You don't have such a situation in the low Prandtl number regime. And there is no such mechanism that you can translate into this regime yet. So there is no well understood way to have dynamo in this regime. But we know there is dynamo in many situations. And that's also, as I said, it's the relevant regime for protoplanetary disk. They start to have simulation now showing a dynamo effect in this regime. But they have to push the Reynolds number to very large values. And you see that the structure of the flow they get in this regime is quite different from the one that we have in this regime. It's qualitatively different. And we may well be more in this situation for protoplanetary disk. So you can actually make a one-to-one comparison between our result and their result. So here's a snapshot of the case I described before. So you see that the structure of the field especially is very similar. You have folded structure in the field. That's again suggesting, so not only do we see the PM effect, but the qualitative feature of the flow are similar in this regime. So Jake Simon kindly gave me a snapshot of their 0.25 simulation. So here's a snapshot of their flow. So you see that here, because the Prandtl number is smaller, you have larger structure in the magnetic field than you have in the velocity field. Okay? That's where we stand in the MRI business. And that's where they got in the dynamo, in the homogeneous turbulence community before they see a dynamo growing. So there is a big difference that we have to cover yet. So now let me mention a speculative scenario that may occur, at least in the large PM case, in MRI-driven turbulence. So this has been suggested by François Rincon and collaborators. So what may happen? But this is something that has to be tested. First, you have large-scale forcing by the standard MRI linear modes. So it's confined to this region. It seems to be what we see in the simulation. So that established a turbulent cascade towards small scale. And then small-scale dynamo a la Chekochin kicks in and raises the magnetic field, back reacts on the saturated state. And that's how you get the PM effect. So whether or not this is actually a good cartoon of what happens is still a matter of probably many years of work, but that's something to investigate. And there are hints that something like that could happen. So can you improve the realism of this very idealized setup that has probably very little to do with accretion disk? So first you may want to include density stratification in these sharing boxes. So it's very time consuming. We're speaking of millions of CPU hours to get to the same resolution. There are also issues associated with the boundary condition that I will not come into, which are delicate to handle. So there have been a first studies recently published by Sean Davis, Jim Stone, and Martin Pesa on that, where they've looked at 3 cases and varying the Reynolds numbers and Prandtl number. And that's the time history of alpha. So there seems to be an effect of the dissipation coefficient. There are very long-term variations here on alpha, the reason of which is not clear. So it's only starting. More needs to be done on that, in that direction. One thing that seems to emerge out of this result, and a similar paper that was published by Shi and Krolik recently, was that you have a butterfly diagram. If you look at space-time diagram, you seem to see a large toroidal field generated in the mid-plane, like here, and then rising toward the top of the disk. It's something that has been noticed since the early 90s, and that that seems to be a general feature of this simulation. And there are speculation of whether this can drive a dynamo mechanism. It seems similar to a self-sustaining cycle that Le Sueur and Longarity found in unstratified boxes. Sorry? Sorry? Yeah, Le Sueur and Ogilvy, sorry. That they found in self-sustaining cycle, they found the self-sustaining cycle in unstratified boxes elongated in the vertical direction. So there are speculation as to whether this is operating. But it could be an avenue. Can you do global simulation and study the effect of small-scale dissipation? A quick estimate of the resolution you need to reach the same sort of resolution is prohibitive. We're speaking of 10,000 cubes sort of simulation. So it's impossible, and it will remain impossible for many years to come. So global simulation will always be under-resolved in the sense of properly studying, have a proper handle on small-scale dissipation. So now let me come back to the issue of numerical convergence. So now everybody is testing the convergence of his numerical scheme for all the situations that I described before. So let me try to summarize what's going on. So without net flux first, so the result we obtained were confirmed by different groups. The origin of this decline, I argued, is not physical, but its origin is not understood. We don't know why alpha seems to be decreasing with resolution for this particular setup. What we learned from this simulation, though, is that this simulation without dissipation, they appear to behave as if they have an effective Prandtl number larger than 1. You can measure the dissipation in this simulation and translate that into dissipation coefficient. It appears that the effective Prandtl number is larger than 1. You can do the convergence study with net flux. So again, I separate in toroidal and vertical flux. And here, it seems to be converged. It seems like as you increase the resolution, you don't have such a problem. You get a well-defined alpha. You have small variation, but they are not dramatic. Not as dramatic as what you have in the zero net flux. They tend to show a little increase in alpha. That's true for both for the toroidal and vertical flux. Again, there is no real explanation for that. You can do that game, play that game in stratified boxes. So far it's been done only without net flux. And again, so it's Davis and Stone and Pesa from, the alpha value you get is well converged in resolution. She, Krolik, and Rosette found the same. So it appears even to be better in stratified simulation than it is in unstratified. So now comes my first bold statement. Should we really care about that? What do we learn from this convergence simulation? The evidence we have so far are that simulation without explicit dissipation, they behave differently from simulation with explicit dissipation. So I gave you an example with these fixed PM simulations. You can do things a bit more quantitatively. Simon et al., for example, they quantified not only the effective Prandtl number, but the Reynolds number, the effective Reynolds number of their simulation from this set of parameters, about 4,000 with a Prandtl number of about 1.6, and they have vigorous turbulence in that case. Now, if you look at simulation with explicit dissipation and with similar parameters, you have no turbulence. It's a completely dead case. So it's a qualitative difference in the structure of the flow. It's also difficult to relate the numerical convergence, whether or not you converge, with the PM effect. You have situation where you have no numerical convergence, a zero net flux situation, and though you see a strong PM effect. And you have other situation where you see numerical convergence, So you may argue that, well, everything's fine, I have my alpha value. But then you put numerical explicit dissipation, and you see again a strong PM effect. So what is the meaning of this alpha value you get in this simulation? So in practice, we shouldn't be too surprised of this work, because what we do in practice in this simulation is we let numerical simulation under the structure of the flow below the grid scale. That's what we do in practice. Numerical dissipation is a subgrid model, and we're using it without validation. So we should be very careful in making statements and drawing conclusions out of that. So now that I told you that everything you do without dissipation should be taken with caution, you can go back in the literature, and here is my blacklist of everything that you should discard from many. So more seriously, you need to be careful. The value of alpha that you get out of this simulation is not the value of alpha in protoplanetary disk. It doesn't constrain the value of alpha. You don't constrain the value of alpha in protoplanetary disk out of this simulation. Okay? And the quantitative estimates that you get out of this simulation should be taken with care. Okay. I'll take 3 examples that have been discussed in this meeting already extensively that are famous results related to the issues we are interested in. And that were based on numerical simulation associated one way or the other with the MRI, which have no control dissipation. I want to discuss these results one after the other and try to discuss them in the context of the result I just showed in the last 40 minutes. So first, the layered model simulation of protoplanetary disk. So there have been a few papers, the most famous of which is by Fleming and Stone. So they've taken, and you're all familiar with this result, I'm sure. So they've taken the Zeus code and do stratified simulation, imposing a fixed profile for the resistivity. They used a large resistivity in the midplane to mimic the presence of a dead zone and make the Reynolds number, the magnetic Reynolds number, decrease from about 1,000 in the midplane to values of a few million at the upper edge. There is no viscosity in this simulation. I'm sure you all know that what you get is you have sustained turbulence in the upper layer of the disk, here and here. Then you have the dead zone where the Maxwell stress gets down, but you excite motion in the dead zone because of the activity in the layered zone. And so you get motions that result in a non-zero stress, Reynolds stress in the midplane. And this is important for planetesimal formation and planet formation in general, because you want to know what happened in this dead zone. So what happened now? What do you do if you try to interpret this result in the context of what I just discussed? So in the midplane here, you have a very large resistivity, a physical resistivity, that damps the linear modes. The viscosity is very small. It's numerical, so it's much smaller than the resistivity. And in fact, what you're doing is you're damping the MRI modes because of this resistivity, and you're simulating a very small Prandtl number flow. So now, as you go up in the disk, you'll have a transition layer where the physical resistivity becomes of the same order as the numerical viscosity. So you'll have PM of order unities. And then up in the disk, the resistivity associated with this Reynolds number is much smaller than the numerical resistivity. So what dominates the flow is actually the numerical resistivity. And we know from the studies by Simon and others, that what you're simulating in fact here is a situation where you have an effective Prandtl number a bit larger than 1. And so one need to be careful here. What are we simulating here? Are we seeing a PM effect, the sort of which I described earlier in this talk, or are we seeing rather than a dead zone? Because a dead zone would be a low PM region, but stable to the MRI, with on top a low PM turbulent flow. Because the PM, the magnetic Prandtl number will be very small in this flow. So qualitatively, it may be different than what we are simulating here. So it may drive, although the fact that it drives motion to the dead zone is very likely to remain, the structure of the flow that it drives in the dead zone may be different, qualitatively different.
The numerical resistivity is bigger than numerical viscosity?
Yeah, so there's a mistake here. It's actually the opposite. It's a numerical viscosity that is probably a bit bigger than the numerical resistivity.
How do you know that?
So we know that from studies by Jake Simon, for example, who has tried to quantify the numerical dissipation in such flows, in MRI turbulent flows. And we found that in general, in all of these simulations of turbulence, MRI turbulence without explicit dissipation, the structure of the flow is qualitatively similar to a large PM flow. You have elongated structure, and when you measure the dissipation coefficient, when you try to estimate this dissipation coefficient, you find that the viscosity, the numerical viscosity, is in general a bit larger than the numerical resistivity. Okay. So there is a typo here. It's the opposite. What you need to have is you need to look at this number. So now I'll move to the second paper. So that's the result by Richard and John Papalouizou, that you have stochastic migration of small mass planets in turbulent disk, and the reason is that you have density wakes going close to the planet and affecting the torque on the planet. And because these wakes are of an amplitude similar to the wake that is generated by the planet, it results in a random walk of the planet. So you can think about two issues here. First of all, the turbulence that you have in this simulation is entirely set, the saturation is entirely set by the numerics. It has nothing to do with, it's what's set alpha. So you have to take that into account when you calculate, for example, stochastic migration rate. But you can view this problem the other way around. You can say, look, the numerics are giving me this value of alpha, and I know it's about the same as the value I expect from the lifetime of protoplanetary disks. So it's supposedly it could give me the right answer, and it would give you the right answer provided you treat the large scale properly in this simulation. So do you treat the large scale properly in this simulation? And we don't know. There have been no systematic study of how the large scale look like in simulation without explicit dissipation, and we should compare how this large scale looks like in simulation without explicit dissipation with simulation with explicit dissipation. This is important, I think, for the credibility of global simulation on the long term. So there have been only one such attempt to look at that by Sean Davis et al. Recently. So this is in local unstratified or local stratified simulation, and so they have two per spectra, one with dissipation, one without, and you see that they differ strongly at large scale or small scale, but they are not so much different in the low K part of the spectrum. Okay, so this is a first indication. We should do much more, because here there are also differences in the alpha value of these two Ks. So I don't know how far we can interpret that, but we need to be careful. And some work need to be done, some more work need to be done on that. So the last and final paper I want to discuss is this famous Nature paper by Johansen et al., in which through the combined effect of the MRI, the streaming instability, and self-gravity, they found the formation of serious mass bodies, as shown on this movie. So again, here there are some issues as to the role of the MRI and whether it's treated properly. So the role of the MRI in this simulation seems to be to create a large-scale pressure bump, which has been associated with zonal flows in this paper. So Johansen, Udin, and Klar recently did a systematic study of these zonal flows, and they have a set of simulation with controlled dissipation, and they seem they've shown that the structure of this zonal flow doesn't seem to depend on whether or not you have explicit dissipation. They found the same characteristics of this flow in the presence of dissipation. So that seems to be okay. However, on the small scale, it is not clear that they are treating the structure of the flow properly. What you expect is that these bodies, when they will form at scales that are well below the resistive scale. So you don't expect large fluctuation of the magnetic field, but they will form at scales that are much larger than the viscous scale. And that's not the case here, okay? So it's reassuring that now they have this new paper, and Andrew is going to speak more about that, in which they found collapse even in the absence of the MRI. So it appears that the MRI is not crucial in this for this scenario to work. I'll be cautious about the estimate of the mass that they have out of this paper. So now, here are my conclusions. So small-scale dissipation is important in local simulation. It is important in your simulation. There seems to be a broad result that emerges. Alpha increases with PM. We have some hints of convergence now, but much more needs to be done. We are very limited to the parameters we can have access to, and we'll never be able to access the limits of real disk. And because of this lack of convergence, we don't know what alpha is in real disk based on numerical simulation. Now you have questions. So although the small-scale dissipation is important in local simulation, we don't know whether it's important in real disk. It's again because we don't have convergent result. So it may just be all crap, what I told you for about 45 minutes, okay? We don't know what happens really. And moreover, all of the thing we've been able to study easily are the IPM case, and because that's where the dynamo is most efficient. There have been very little studies of the low PM turbulence that is much more relevant to protoplanetary disk. And I'll stop here. Thank you.
In the high resolution, very high resolution simulation, do you see scales that are small enough that the turbulence is effectively homogeneous, and so you can sort of carry over these results that have been done in the forced turbulence limit?
It's still a low PM, so it's PM equal 4, so you don't have a very large scale separation between the resistive and the viscous scale. So.
Because I'm more wondering whether you get small enough, just the properties of the turbulence look exactly the same as if there was no shear.
No.
You still see the shear as...
I think you still see the shear everywhere in this simulation, which is the limit, yeah.
Regarding the question of the existence of a dynamo effect in the zero net flux cases, how can you be sure of finding the dynamo solution if it exists? I mean, it is a nonlinear dynamical system. It can return to the zero state.
We cannot be sure, I think. We are not even sure that I mean, although we think we have a quasi-steady state, we cannot be sure that it's going to persist for more than the duration of the simulation. So we're not sure. Or I don't know of any way to be sure.
But is it safer to restart from previous turbulent simulations rather than to...
So I've checked, I've done some checks of that. So far I haven't been able to find any case where I see a strong difference between how I start my simulation. I've also, so I've tried to start the simulation instead of having a vertical flux with oscillating sine, I started with a toroidal flux with oscillating sine. You don't find a difference. I know that Geoffroy, for example, is not starting with such a configuration, right? You're starting with a noise at quite a large amplitude. That doesn't seem to matter too much. We can only make some tests like this one and increase the duration of the simulation as much as we can.
Could we have any information of, with the fluctuations of the alpha value?
What do you mean?
So you see that in time you have fluctuations of alpha, and from these fluctuations, could we have any information into the system?
I don't know. There appear to be a correlation between the amplitude of this fluctuation and what alpha is. There haven't been many studies of that. I don't know.
I think you demonstrated very nicely that the PM dependence we see both in zero net flux and net flux simulations in the local box can be related to the excitation conditions of a small-scale dynamo, as is studied by Shiko Shihin and collaborators. And I think that a possible way around this might be the stratification indeed, because you see that the sun has a strong magnetic field and a large-scale dynamo. So it has been shown recently that a large-scale dynamo can even be excited at small magnetic Prandtl numbers. And that might be a way around this whole PM dependence.
Yeah, I agree, and that's what's the early result of stratified box system to suggest as well. You know that.
So in this large resolution simulation, you're saying that you have injection of energy at large scale, and that explains the kind of Kolmogorov spectrum for the velocity field. But how can you explain the bumpiness of the magnetic field?
I don't know. It's again consistent with small-scale dynamo. You would if small-scale dynamo operates, you would expect energy to grow at small scale and then back react. The problem here is that the magnetic energy is larger than the kinetic energy.
If you have a small-scale dynamo, you would see it below the viscous scale, presumably. So it should be.
Well, but we don't have a separation of scale.
Yes.
It'd be much better to do that at PM equal 32, 64, 128 or whatever is enough to see the separation of scale. Yes.
Sebastien, in these low Prandtl number cases, what sort of values are people finding for the Alsacer number, which of course then determines whether the linear modes of the MRI are being quenched?
So you're referring to the paper by Jack Simon?
For example,
I think they have pretty large Alsacer number in this simulation. It's above 100. Yeah,
okay.
so they've done a pretty careful study of that. It seems to be high enough.
and in the other lower Prandtl number cases that you referred to, where you're finding turbulence being quenched at Prandtl number of 1 or 2 in some of the earlier work?
Well, then of course, then is how do you define the Alsacer number? Because I don't see turbulence.
As the turbulence runs down, of course, you get to a stage before it dies where the Alsacer number does.
Presumably, it becomes of order unity and then smaller, and it goes to 0.
Yeah.
That's why maybe when you go to much larger Reynolds and magnetic Reynolds numbers, you start with larger Alsacer number. You know to better. Although I should mention that the magnetic Reynolds numbers of order a few thousand that we have, they start to be comparable to the protoplanetary disk Reynolds number you expect. So, although we are very far from having the realistic viscosities, we are not so far from having realistic resistivities.
But the Alsacer number is defined with the vertical thing speed. So
Yes.
Jake Simon's work, it must be 0 initially. The AZ is 0.
Yeah, I think it took the the entire Alphen speed, the sum of the
That's not
components.
That's not the definition.
Yeah, I don't know what its
So
vertical
very
Alsacer
small
number
Alsacer
is.
number region still.
Sorry?
So it still must be a very small Alsacer number.
Initially it is, yeah, then I don't know what it is in the saturated state.
So actually, just maybe if I could take the last question,
No.
prerogative. So if we take it at face value that the small scale dissipation controls the large scale dynamics, if we connect to Mark's talk, shouldn't we really be doing Hall and ampolar diffusion, and will the convergence be different in that regime where the issue is completely different than always?
Yeah, it's an open question.
Get busy, Mark. Okay, I think we should move on to the next speaker. So next up is Pierre-Yves Langretti.